SwayamPrabha. Digital India. Educated India.
So, in the last class, we were looking at programming philosophy, of microcontroller in general. So, microprocessor has different kinds of interfaces available, and we saw some general philosophy of programming interfaces also in the last part, where we looked at control registers and actually working registers. So now in this class we will look at different kinds of interfaces that are available, and typically with some examples we will look at their little more detail about what is their utility, how they can be used for useful applications. Okay, so let us begin. Different kinds of interfaces possible. Okay. As we can see here, so first is digital input output interface. Okay, the digital input output is the most common interface that is there in all microprocessors, okay, or microcontrollers. So this interface allows you to exchange the data in the digital format, either input or output, with the external peripherals. Okay, say for example, if you have a indicator, so some LED light, okay, that you need to glow after some process has happened or indicating something has happened, then you can use this digital input interface. Then you can have limit switches in the operation you want to kind of control the application such that it doesn't damage the system. So when this limit switch is reached, that is an indicator that your operation beyond this point is going to be harmful. So when that switch is reached, we will switch the system off or do something to save the system. Okay, like that you can use these digital input output interfaces. Other very important application for this is stepper motor running. Okay, there are different interfaces available for stepper motor running nowadays. You can use digital input output as a most basic kind of interface with amplifier, or you can also use PWM interface nowadays for this. Then you can use this for direction control in the servo motor control. So there are ample applications, and this is most important interface to be used. So say for example, we saw 7-segment display in our previous classes. So to program that 7-segment display, you will need this digital input output interface. By using that, you can display some numbers or some data to the user. So this how this interface works is very simple actually. You know the registers now. The registers, if the pins of the registers are made available to the user, normally they are not available to the user. So given a register, if the pins of the register are made available to the user, then user can use those pins for where the data is high or low. That depending upon if the value in the register is 0 or 1, the pin will go high or low, and that is what is indicated and used by the external user in some way. And you can have some kind of a logic to have the facility for this wire to kind of input the data to the register as well. Okay, then reading and writing to this digital input output is done by using some kind of a control registers by programming control registers first, where you define whether the given register or digital input output port is, so to say it is called, is used in the input mode or output mode. So for that you need some kind of a control registers typically. Now let's have a look at little bit of more details about this TIVA launchpad. That is what we will is optional, but we'll use in this course as a hardware for this TIVA interface, this TIVA board that is picture is seen here. The F port, for example, in TIVA is used for LEDs online. Some part of the LEDs, there are so these 3-4 LEDs that are there on the board. There are 3 LEDs actually. So R, G, and B. These 3 LEDs are there, and they are connected to some TIVA port. Okay, connection pin diagram is shown in this TIVA datasheet. Now the way this TIVA input output pins, other pins, okay, this is F port, but there are some other ports available on these pins. And interestingly, this is very compact and more kind of a modern ARM architecture, as we saw, based interface or a microcontroller interface for this digital input outputs. So let's have a look at little bit more details about what facility this interface gives in TIVA. Okay, so before going to the ADC, we'll look at the TIVA in little more details here. Okay, so you can see that the TIVA peripheral driver library, okay, this particular file, PDF file, will give you all the details about the functionalities, or the API library is there. So this is a driver library. These are API functions are there. This function description is given in this file, and in this you have the this is a TIVA datasheet for the TIVA. So this is a microcontroller datasheet, and this datasheet also gives you the details of the GPIO interface. So this so depending upon this programming philosophy, you'll use either of these two for the programming. Say for example, if you use the TIVA microcontroller datasheet, it will have all these different registers that are defined here. So let's say GPIO interface, if you see here, general purpose input output. Okay, so it will give you the different registers that are used in GPIO interface, for example. Okay, and these some kind of a block diagram of the architecture of this general purpose input output interface, and so on and so forth. All the registers where you can use for programming and controller that will be given here. Okay, so in this you'll have directly functionalities given. So if you are using directly API functions of this driver library, then you don't need to worry about these different registers that are control registers or working registers. You need to understand how these functions are written. Okay. And interestingly, if you see this TIVA general input purpose input output interface, it has this port. This general purpose input output pins have a mapping possible. Okay, so for example, these pins can be normal function or alternate function selection is there. So where you can select it as a say for example QVI interface pin. Okay, so this for these digital pins, you can configure these pins to work as a quadrature encoder interface, or they can work as a PWM pins. Okay, so this configuration is done via two ways. One is by using this kind of a control registers that are given in this datasheet of the TIVA, the chip, or the functions. Okay, so for example, if you go to this GPIO functions, then it has some introductions, and there are different functions that are given. Okay, and some of these functions are like having this pin configuration. If you see here, there is a pin configure kind of a thing. So you configure this pin for different types of pins. Okay, it can be as a ADC pin, or it can be as a general purpose input output pin, or PWM pin, or QEI pin, like that. So this function you can directly use then for the configuration. Okay, so like that you start reading through the data sheet and understanding these different functions. So if you go through details of this function, you'll find a way to use it and write it. And then there are these of course there are these programming examples that are given. These are functions here, list of functions, and programming examples. And then you can directly go to programming examples and like see these sample programs and figure out, okay, what changes you need to make to do it for your own kind of a purpose. Okay, so let's get back here. So that is about GPIO, general purpose input output interface. So in this particular case of TIVA, that interface has possibility of many different functions that can be possible for that interface. Okay, so you can program the pins. So this pins are programmed. That interface is GPIO, but the pin can be programmed to have different kinds of other interfaces possible there. Okay, which may not be there in all the microcontrollers. Okay, these modern microcontrollers, which is ARM based microcontroller, TIVA has that functionality. Okay, or some microcontrollers for XCP100, for example, will have only input output pins. They are not non-configurable. Okay, you cannot change their functionality to use them as a PWM pins. Okay, so depending upon what is written in a data sheet and what is of your interest, you can start using them. Okay, now let's look at this ADC interface. So this as the name says, is analog to digital kind of conversion interface, and it is used for reading analog sensors. So you have analog sensors like temperature sensor, pressure sensor, or potentiometer, accelerometers. They have analog output, and that analog output needs to be sensed. Or you want to say some resistor value, resistance resistor is there, in which when the current changes, like you want to sense the voltage there. Those are kind of places you use these ADC sensors. You have the strain gauges, for example. So there are many different utility for this analog to digital conversion. And how this analog to digital conversion happens is by using a comparator. Okay, you have this digital to analog conversion interface first, which uses a digital value given by microcontroller and processes it to give analog output. Okay, how does it do that? Maybe we have some something to show. Okay, I'll show you some stuff later. So this digital analog conversion is done first, and analog value is available. Now this analog value on one of the pin that is available is compared by using op-amp comparator with the analog value that user wants to sense. And when these two values match each other, then the digital value that is supplied to this pin, which is used for comparison, that digital value is going to be the value for my analog to digital conversion. Okay, so this is how the analog to digital conversion works, by using the comparison with value that is generated by the microprocessor itself through digital to analog conversion. So this interface is also very popular. We need to use it many places in mechatronic systems for various kind of sensing application. And this is IoT, for example, is very much in IoT. This is of a great value, this interface. A lot of values can be sensed, analog, like temperature or like acceleration in the places can be sensed, and that can be used in the IoT way to monitor some situations around any machine. Okay, Then this is a very important other interface called quadrature encoder interface. This interface basically is used for encoders. So we have seen in the sensors lecture what are the encoders. So those encoders, if you directly want to interface with the microcontroller, you will use this quadrature encoder interface. This has, as we saw before, it has signals of the form A and B, where these both are kind of pulses which are 90-degree phase shifted. Those A and B are taken as an input to this quadrature encoder interface, and then they are processed to generate a number, or they are counted to get a number which will correspond to the position of the encoder. So this is nowadays very useful interface, because encoders are digital sensors for position. Instead of using your potentiometers, encoders would be preferred, because they will have absolutely no noise, because they are digital in nature. Okay, and that has a lot of important applications in position control systems. Okay, so a lot of mechatronics positioning stages would use encoders, and for those encoders this interface will be very useful. So printers or machining systems, CNC and others, they will have these encoders. Then this we'll discuss this more details about this interface and how to program for particularly for TIVA. We'll discuss a little bit more detail in another class, and that can be used for actually programming this hands-on. You're training your own kind of a TIVA microcontroller for using this interface along with the motor that is there in the kit. Then you can have serial and other kind of communication interfaces which are nowadays available, like a USB communication or CAN communication. Okay, so this control area network kind of a communication interface that has been specifically designed for automotive kind of a control systems. Okay, so these are all different kinds of interfaces that can be possible for serial and other communication. You can have some kind of a Wi-Fi kind of a interface, or wireless communication kind of interfaces also are possible. So although in TIVA it is not there, but there are other kind of microcontrollers where you can find the direct inbuilt interfaces, or with TIVA if you want to use, you can use Zigbee kind of wireless devices to communicate with. Okay, then so this is where, like I was talking about, this digital to analog conversion interface which is there in the analog to digital conversion interface. So to make ADC work, you need to have a DAC inside ADC. So this DAC interface can be also used separately, So typically this interface would work very simply. You can have this circuit which is some kind of a op-amp with these dividing resistors. Those provide this current here, and then this current is amplified, and you produce this analog voltage output. Okay, and this current is proportional to the digital values that you are supplying at every each of these resistors, and these resistor values are so selected such that the calculation will show that your when this digital value is changed linearly, the analog output voltage will change linearly. Okay, so this is like a summing op-amp which will sum up all these different voltage which are coming here because of the differential currents that are proportional to the the digit that digital value that you provide here, and higher the digit, say D0 is the least kind of a significance digit, its resistance will be very high, and the most significant will have a low resistance, so that it will get like more representation in the summation. Okay, so this is typically the digital to analog interface works. Okay, and this is not very wide, but some applications where you want to run like you have a motor which you want to run, and it is having an amplifier which is analog to analog kind of a conversion amplifier. There you will need a digital to analog interface. Otherwise, typically for a running motor we use PWM kind of interface, which we'll see. And the main drawback, or what you say, not drawback, it's a characteristics of the digital output is that it will have this stepping kind of a behavior, of course, because your voltages or your digital values are going to be in discrete kind of a form, and depend upon the number of bits that you use for this conversion. So you have a 3-bit conversion, then like the least count will be 1/8. You'll have that much kind of a error in conversion. Like that you have this possibility. So this is called quantization kind of errors typically that they exist in these systems. Now we come to this PWM interface, which stands for pulse width modulation interface, and this is very important interface for mechatronics engineers, because this interface you can use for driving many different kind of actuators, okay, or you can use it for clock generation kind of application for external peripherals. There are many different ways this interface can be used, but the most important is driving the actuators by this interface. Why this interface is used for driving actuators, we will see that. So how this interface works is basically it uses a clock signal of a microcontroller and divides that, or uses that to generate some kind of pulses. Now let's first understand what is this pulse width modulation. So this pulse width modulation will be where you have a pulse coming on the pin, and that at some frequency, say maybe about a kilohertz or 4 kilohertz kind of a frequency, the pulse comes, and the pulse has typically clock pulse will have 50% duty, means like the clock pulse will have 50% on time and 50% off time. The PWM, you can have this different possibility of varying that duty, in the sense you can say this is a 10% PWM or 10% duty PWM, where the on time can be changed, okay, depending upon what is application or what is the requirement. So this PWM interface provides a facility to change the frequency and on time for the pulse, okay. So we'll see. So the more programming details will be there in the microprocessor datasheet, microcontroller datasheet, and we'll have a look at in the further classes. Okay. So this now let's look at how this motor, why motor needs PWM interface. Okay. So if you want to drive an actuator, okay, so you need a driver for amplification, okay. So say, because you cannot say, okay, I'll connect my motor directly to my microcontroller and it will start running. No, you imagine, like, no, you cannot connect the ceiling fan, for example, to your microcontroller and expect it to run, right? Because typically these motors will require like larger power, okay. Microcontroller are supposed to be like very low power devices. They'll provide hardly any current for these applications to run. So what we do is we amplify the current that we, or current or voltage, whatever you want to say, that we get an output from the our microcontroller, and then provide it to the actuator. And suppose, let's say, if we use some kind of amplification here, say let me get an interface, right. So if we use say some kind of a transistor based amplifier, for example, okay, so typically the amplifier is required. So this will be the kind of a configuration that you will use. So microcontroller, the output goes to amplifier amplifies the thing, increases power and gives to actuator, and then actuator drives your mechanical system, and the sensors will sense the feedback, and it will provide that feedback to microcontroller, and microcontroller will take some decision to process this and give power to the amplifier. This is a typical kind of a it's a loop in which the microcontroller, your mechatronic system, would be working. Now so we are focusing on now this amplifier unit here. Okay, so what kind of amplifiers we will use? Suppose say we have a transistor based amplifier. Okay, so say ULN 2003 chip for driving stepper motor is there, like that we are using some kind of a transistor amplifier. Okay, so if we use this amplifier in the servo motor, okay, so what we are talking here is, right now when we are talking in this actuator driver interface, we are typically the servo motor we are talking here, not a stepper motor here. And this servo motor, not really this aero modeling servo motor, so there are different kinds. There is a different, although the terminology is same, what we are talking about is DC permanent magnet DC motor. We will use this term permanent magnet DC motor rather than servo motor. Okay, so when we have to drive permanent magnet DC motor, then if we use this kind of a circuitry, and then here we give from our digital to analog conversion. Okay, that voltage we give here, then that voltage will be amplified, and you get some kind of a current to flow through this load. Okay, so what is the problem with this kind of a interface? So if you think about, what happens, we need to go back to the transistor characteristics. The transistor characteristics tells us that unless some base bias voltage is there, you cannot fire the current through the collector. Okay, so that means you need to provide some kind of a bias voltage to the transistor before we expect some current flow to happen in the motor, which is one drawback, that okay, you have this kind of a dead band that will come. And the other thing, that is kind of a main reason you'll have a problem here, that okay, you go below certain kind of a voltage given by the analog to digital digital to analog converter from your microcontroller, and then beyond this only the motor will start running somehow. Okay, and other problem is where see, when this is very low, this voltage or the signal that is given from the microcontroller is very low, you will have a lot of noise that will be seen. The signal to noise ratio will be very high for the low signal. Okay, low value of the voltage that you are providing, and that would drive some kind of your actuators will get driven with that kind of a low signal, that is the amplified version of that signal will go to the motor, and then motor will start making like a noisy behavior. Okay, so this is main problem here. And other thing, of course we need to think about is okay, the other side we don't have same kind of a characteristics, and then other side we'll need to see okay, how do we reverse the direction of the motor. Okay, we cannot drive current negative by the same kind of a circuit. We need to have something else to do to reverse the direction in the motor. Okay, so how are the solutions for this problem done? By using pulse width modulation is what we need to think about and see. So you pause and think, okay, how this problem can be solved by using pulse width modulation, where pulse is of a fixed voltage value. Okay, but the pulse duration can be changed. So think about that, and then pause here for a while. After you have gathered your thoughts, then you can go forward. Okay, so ponder over these questions. So as I have told you, the pulse width modulation has this idea where the on time period can be changed. Okay, so now what happens when we do this kind of a thing, going to an amplifier, the same kind of amplifier we use. So we use same transistor amplifier, but the now, instead of giving analog as an input to that amplifier, we give this changing pulse as a input to the amplifier, and this pulse is given at a very large frequency. So large frequency is that in such a way that your motor output, okay, it does not respond to these pulses. Okay, what I mean here is that, see, these pulses can be changing at a frequency of say few kilohertz. Now imagine if your motor is given the input at that kind of a higher frequency, motor has a large inertia. Okay, the frequencies of the motor, or then bandwidth of the motors, will be typically in a some few hertz kind of a range. And when it is given kilohertz kind of a signal, what motor sees actually is the average value that is seen here. Okay, so how this average value is seen will also be clear. This is based on basically because the inertia of the motor is much higher. Okay, and suppose we give this input to our amplifier, then what happens is the value is always operating point is always here. Okay, because values are either 1 or 0. You can see that this value here is either 0 or 1. Okay, this is 1 here and this is 0 here. So but only the period of on time is changed. This is a time period, and on time out of that is changed. Okay, so since the on time is changed, and this value is fixed, now this the noise, if you talk about that, we said is in the small range here. So we are not, since we are operating at this point, the noise is not going to bother us anytime now. Okay, so noise will be much smaller than this value here. Okay, so the voltage value that we are providing, since it is either 1 or 0, the noise levels are relatively low as compared to that, and that's how we get rid of the noise problem here. And then this how do we change then the amount of power given to the motor? By changing the on time. Okay, as you give on time lesser and more, like you see that the power delivered will be more or less. Average value of the current that will be flowing in my motor is going to change based on the on time, or how much time I give this during the cycle of the PWM. Okay, so so this mechanical inertia of the motor, it does not respond to these pulses, is what we may make use of this fact, and the motor can see then only the average power delivered. Okay, so this is how this fundamental principle is used for driving all your actuators in a very noise free kind of a way. And how do we reverse the direction? We use the edge bridge circuitry to do this. Okay, so this you might have already, some of you might have already used this in programming your some hobby motors or something like that. So these are the advantages that are listed for the PWM. Okay, then how do we reverse the direction is using this edge bridge. And edge bridge, there are this lot of these different chips available for edge bridge kind of functionality, and it works as an amplifier and direction reversal. Both functions are done in one kind of a chip. Okay, and this is very good ideal kind of a thing for motor control, digital control of the motor. And there are many advanced features could be available in other kind of chips. Okay, so this edge bridge has a very simple way of switching the transistors and reversing the direction of the current in the motor. Okay, so this is transistor based switches are realized here, and this is one way direction and this is the other way direction reversal by switching S1 and S4 first and S3 and S2 the next for reversing the direction. Okay, so you can see this is a configuration of typical edge bridge. Okay, so it has say some gates to operate and things like that, and so one can figure out from this kind of a block diagram of the chip how this chip can be interfaced with your microcontroller and what is to be connected to motor to kind of drive it. Okay, so think about this, we'll have this important exercise to be done. So there is inputs here, and then there is an A kind of a signal. Okay, E and A is kind of a signal, enable kind of a signal here. Okay, and then there are these outputs that are coming out of this edge bridge. Okay, so you can see how many motors can be driven. See here there are 1 2 3 4 outputs are there, so you can drive 2 motors. One motor can be connected here and another motor can be connected here, and then suppose I want to reverse the direction, what should I do? That you can figure out from this kind of a diagram. Okay, so think about this. Then there are these some kind of a sensing terminals also are available here, so which can be used by user for something. Okay, so you think and figure out, it's not very difficult when this kind of a diagram is given to figure out, okay, how this current is going to flow for one particular direction, which transistor should be on. So these transistors here, you can think them as the switches, and then the switches are operated when this output of this AND gate becomes 1. Okay, that is a hint to think about. Okay, so then you can figure out how things will be working here. Okay, so you pause and think about this part. Then there are many different kind of drivers that can be possible for this edge bridge, or depending upon kind of a motor. Okay, so DC permanent magnet DC motor can be driven by the edge bridge, or stepper motor can be driven by this some simple ULN transistor amplifier. And important issues to consider is power requirements for the motor. Okay, available control signal. Okay, especially the voltage output amplitude. Okay, and this power requirement and motor voltage compatibility should be seen. Okay, power, not only power but voltage and current compatibility to be seen. So driver also should be compatible with the motor. Say if motor is requiring 2 amperes of current, driver should be providing more than that. I mean, typically 3 or 4 amperes of current rating should be there for the driver, like that. And also, of course, voltage compatibility should be there. Then number of motors to be driven would be other issue that we can see. Then robustness requirements. Okay, so there are some advanced chips that are available to, or advanced drivers that will be available for giving you some additional functionality. Okay, then typically brushless DC motors, there are some controllers available, for example from Maxon motors kind of or Faulhaber. There are 2 major players in the international market which are having excellent quality for these motors. Okay, then there are many different companies. Siemens has controllers, or so you can look at yourself, there are a lot of motor drivers available. Then you go for AC servo motors when you have very high power or torque requirements. Then we use Quanzer analog amplifier. This is an analog driver. This is not a PWM amplifier. This is an analog amplifier which is used in our double flexure manipulator kind of a system where we want to have a very high very low noise in the system and very high precision positioning requirement is there. Okay, so like that you can have many different kinds of drivers possible. So what you need, basically the fundamental knowledge is about what we have seen. Okay, how do you read the data sheet and utilize the information to interface these different things. Okay, so you need to see mainly the current and voltage compatibility, and of course the absolute limits of different things, so that you don't damage the systems. Okay, so this is what we had talked about anyway. And another thing is very important is this response bandwidth. Okay, so the driver should be fast enough to respond to. In many places this will not be a problem, especially when we go for MEMS based kind of applications, no, then this response will be a problem, because electrical electronic things respond much faster. Electrical signals are much faster responding than mechanical motions. Okay, so response bandwidths will be satisfied, like they will be pretty fast for the electrical domain. But when it comes to very tiny systems like MEMS, then the motion can be very fast at the low speeds, low masses. Okay, and then when these motions are very fast, then those bandwidths of that motion can be matching with the bandwidth of the controller, and that's where we need to bother about the response bandwidth of the controller. And these are like some of the schemes for implementation, as we have seen. This one of these schemes we have seen already. You can have a computer or microprocessor or microcontroller, whatever you want to use for the brain or for the control of these. Okay, so this is what is about interfacing different drivers and actuators here. And this we'll see now how these interfaces can be then further used for building mechatronics application. Okay, thank you.